How does the ability of Ubuchi et al. To synthesize high-purity P2 nanotube by increasing the synthesis temperature contribute to achieving an optimized material? And what specific benefits does a high-purity phase offer in terms of electrochemical performance and cycle life? Finally, how can these various findings concerning electrolyte compatibility, synthesis temperature, ion storage mechanisms, and phase stability be integrated to guide future research on developing cathode materials that deliver improved performance, enhanced stability, and greater safety in sodium-ion batteries? How does synthesizing the material at 900 degrees Celsius ensure that its water content is maintained below 20 times 10, and what mechanisms during high-temperature processing contribute to achieving such low moisture levels? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? In what ways does this extremely low water content affect the crystal structure and intrinsic stability of the material during battery operation? How is the impressive specific capacity of 190 mAh G superscript 1 in the charge-discharge range of 1.5 to 4.3 be achieved? And what role does the high-temperature synthesis play in enhancing its electrochemical properties? What experimental methods might be used to accurately measure both the water content at these synthesis conditions and the specific capacity as illustrated in figure 3.19b? And how do these techniques validate the reported values? In what manner do the structural characteristics resulting from a 900 degrees Celsius synthesis contribute to efficient ion transport and reversible electrochemical reactions within the material? And how might these factors interrelate to yield high performance? What potential challenges or trade-offs could be associated with maintaining such an ultra-low water content while operating in the specified voltage range, and how might these issues impact the long-term cycling stability and safety of the battery system? Ultimately, how can these insights guide future material design to optimize both the synthesis process and the electrode performance for advanced sodium-ion batteries? How do the charge and discharge curves of Na-MnO2 differ between the two compositions? Specifically for Na/Na.6MnO2 measured in the 2.0 to 3.8 V range, and for Na/Na2/3MnO2 measured in the 1.5 to 4.3 V range. And what do these differences reveal about the underlying intercalation and deintercalation processes? How does the variation in voltage range influence the shape of the curves, such as the appearance of voltage plateaus, slopes, or hysteresis, and what can be inferred about the reversibility of the redox reactions in these materials? In what way does the different sodium content and corresponding stoichiometry affect the capacity delivered during charging and discharging, and what are the implications for phase stability and structural changes upon cycling? What?